Let me check that it is coming or not. Yeah, I think it's working now. So let me discuss the question again, because this is the, so in this case we are given that a hollow cone of height h and base r can rotate freely about in vertical axis. A narrow friction groove is cut along its surface from the apex to the base. The cone is initially set to rotation with angular speed omega naught. A small block of mass m is released from the apex, slides down the groove under gravity. The block always remains in the groove, it does not leave the surface. The moment of inertia of the cone about axis is I naught. So we have to find out two things. Find the angular speed of the cone when the block reaches the bottom of the cone, and part B, find the speed of the block when it reaches the bottom. So basic figure is already there. So there is a cone and it is rotating with the angular speed omega. The block is initially at A and final position is B. And we have to calculate everything with respect to this point B. And its height is given as h, radius is our r. Okay, so there is no external torque and everything. So here we are going to start with our conservation of angular momentum. So you can say that conservation of angular momentum and we can write that the total angular momentum at any given time with respect to the axis, let us suppose this axis is our PQ, because it is rotating about PQ, will be equal to angular momentum that is associated with a cone plus angular momentum that is associated with mass m. And we are talking about at any time t, not the initial one, because initially the mass is at the apex and that is exactly on the axis of rotation. So initially its angular momentum, contribution of angular momentum of this mass m will be equal to 0. So we can say that total angular momentum about the axis PQ at any time t and let us call this as our L, which will be equal to our angular momentum because of the cone plus angular momentum because of the mass m, and it is at a distance of, suppose, our r, and this is our square, and times omega t. And for this sake of calculation, let us assume that at any given time t, the mass m is at this position and its distance or radius is, suppose, our r of t. So this is the position at any time t. And we can just reformulate. We can write this as omega I naught plus m r square t times omega t, we can take as common. So this is our total angular momentum, and at t is equal to 0, at t is equal to 0, we know that our block is at position A, and at position A the radius, that is r of naught, is equal to 0, okay, because it is at the top of this position. Here radius is equal to 0. Therefore from here we can write that our L initial will be equal to our I naught and omega naught. And after a certain time it is given that the block reaches at the bottom. So we can say at t is equal to capital T, block is at B, and in this case our R of T is equal to our R. Therefore we can write that our L final will be equal to, and we have this as I naught and plus R M, this is our M R square, and let us call this a velocity as omega final. Now we can use the conservation and we can say that our L initial is equal to L final. So we get from here that our I naught plus omega r square omega final is equal to I naught times omega naught. Therefore we can say that our omega final will be equal to our I naught divided by I naught plus mr square multiplied by omega naught. So this is our angular velocity of our cone when the block is at the bottom. So this is our part A. Now we come to our part B, and it is said to be with respect to our inertial frame. So we can say that, and for that we are going to use conservation of energy concept. Okay. Therefore we can say that because initially the block is at a height h and it is exactly at the apex, so there will be no rotational energy, only potential energy will be associated with the block. So we can say that initial energy of block is our potential, let us call this as initial potential energy of the block. Let me put this here, initial energy of the block, that is potential energy. Which will be equal to our mgh. So there is no, we can say, rotational energy, and therefore we can say that the initial kinetic energy is only the cone's rotation. Let us say k of I. Therefore we can say that k of I will be equal to our half I naught omega naught square, and at the bottom the block's potential energy will be equal to 0, and there will be only kinetic energy that will be associated with the block. Therefore we can say that at the bottom cone rotates at, let us call this as omega f. Okay, so this final is our nothing but omega f, and the block has a speed v, and specifically in inertial frame. In the inertial frame, mind it, its potential energy will be equal to 0, block's potential energy. Therefore, we can say that final kinetic energy, let us call this as kf, will be equal to our I half I naught omega f square plus half m v square. Now we can use conservation of energy. Energy conservation, and this gives us that our total initial energy will be equal to total final energy, and total initial energy is equal to the potential energy plus kinetic energy will be equal to our kf, and let me call this as our p of I. So we can say that our p of I plus k of I is equal to our k of f. So we substitute them, we get this as a mgh plus half I naught omega naught square is equal to half I naught omega square plus half m v square, and we can just rearrange it with respect to for our v. So we can say this will be equal to our half m v square is equal to mgh plus half I naught, and this comes as omega naught square minus omega f square. Now it is a simple calculation, and we can just divide by m multiplied by 2. So we get this as our v square will be equal to, and we will left with 2gh plus 2 goes by 2, and this will be I naught by m, and we have omega naught square plus omega f square, and we already know that omega f we already know, so we are interested in finding out this particular term. So we can solve this separately. So we can see our omega naught square minus omega f square. So we substitute our omega f minus, and this is our omega f is our I naught m r square, and this is our I naught, and I naught plus m r square, and this is times our omega naught whole square. So we can take omega naught square as common, and we get this as 1 minus I naught square, I naught plus m r square whole square, and we can take the LCM and we can solve this. So we get this as omega naught square, and we get this as our LCM is I naught plus mr square whole square, and we open the bracket square rather, so we can say this is I naught square plus m square r4 plus twice I naught mr square minus I naught square. I naught square cancel out, and we can take m r square as common. So we get this as our omega naught square mr square, and this comes our twice I naught times r plus mr square, and divided by I naught plus mr square whole square, and bracket closes, and we substitute it in the velocity equation. So we get that our v square will be equal to 2gh plus I naught upon m times omega square mr square and 2 I naught r plus mr square and I naught plus mr square whole square, and our this m and m cancels out, so we get that our v square is equal to 2gh plus I naught omega naught square r square and multiply by twice I naught r plus mr square I naught plus mr square whole square, and we can just remove the square from here and we take this as our square root. So this is our velocity of the block at the bottom. And in this case we can just also say that suppose this is point B and it is lying at the bottom, and just before the block is traveling in this direction, so here it is going to have two components. Okay. One will be the tangential component of the velocity, another one will be our, you can say, the down the groove, and the net will be somewhere here. Okay. And the tangential component will be our omega c times r, and v groove we can say our v groove. This will be our final velocity. So it will be something like this. So bottom, just at the bottom it is going to have two components. Okay. And okay, so this completes both the questions, and next time we will discuss more questions about this rotational motion. Thank you.